Hello everyone. So today I'll be talking about a fairly recent work that is a part of a line of research called compressive tomography that I started at Seoul National University in 2018 and has since attracted many experimental collaborations, and the list is still growing. So the main objective is to develop new concepts and numerical techniques to reduce resources significantly in uniquely characterizing quantum systems, and we shall be discussing these methods and their results for quantum measurements. So we know that quantum information has emerged as a hot field of discussion, and ever since Google published its results in Nature in 2019 for its Sycamore quantum computing chip, the hype has been immense. But underneath this hype, the key foundation of a quantum processor always involves three basic things: the quantum states of the source you use to start any quantum task, the quantum gates or processes you employ to manipulate quantum systems in order to perform those tasks, and the quantum measurements to perform measurements on the manipulated systems to collect data for, say, heralding experiments, measurement-based quantum computing, or analog quantum simulations. So it is extremely crucial that each of these components are properly characterized in order to ensure that the output of the quantum tasks is reliably correct. For practical quantum processing, however, we generally require quantum systems to have large dimensions, and so the complete characterization of such systems becomes polynomially difficult. So how does compressive characterization enter? Well, we know that quantum tasks that we are generally interested in usually run on pure quantum states, unitary gates, and rank 1 measurements. These components are therefore rank 1. Now, in real experiments, although they are not rank 1, they are nevertheless still highly rank efficient objects. So they need much less parameters to describe than, say, d squared or d to the 4, depending on what you're actually characterizing, where d is the dimension of the Hilbert space. So compressive tomography is a fairly recent set of tools developed for characterizing all these rank efficient quantum components with much less resources. The big leap in these new methods that we have right now is that we can do this without any ad hoc assumptions or prior information about the components that are usually unreliable in real experiments. This is very different from the previous compressed sensing methods applied to quantum tomography, where one has to assume some sort of upper limit for the rank of the state that should also be much smaller than its dimension d for significant benefits. So such rank assumptions are really inapplicable in real experiments because of statistical fluctuation, and verifying these assumptions will anyway require more experimental investigation. So in 2019, we discussed the first implementation of such assumptionless compressive schemes on quantum states and discussed various kinds of compressive scaling behaviors for different kinds of measurements on rank efficient states. We also confirmed experimental results with the orbital angular momentum group at the University of Ottawa. We then started looking into applying these schemes on quantum processors. So in 2020, we started working with groups in Moscow and Postec in South Korea to characterize spatial mode optical fibers and photon polarization unitary gates. That's this year. So today, we shall discuss our latest work on compressive quantum detector tomography, CQDT for short, also published this year, which is the first application of compressive characterization of quantum measurements, at least to our knowledge. So, in ordinary QDT, quantum detector tomography, we want to characterize or reconstruct a set of unknown quantum measurements, or POVM. So we begin with a set of probe states that can be easily generated in the laboratory, send them through the unknown POVM, and collect data. Now, in the standard procedure, after collecting data for each probe state, we temporarily, say, forget about the data and decide to send another probe state through the POVM. After sending, say, these square probe states, we then have enough data to uniquely reconstruct the POVM. This, of course, requires a lot of probe states if D is large, but in CQDT, instead of putting aside the data after every step, we consolidate the entire data set collected thus far and perform what is known as the uniqueness certification. Now, this certification checks whether your entire data set leads to a unique POVM reconstruction. If so, no more probe states are needed. At this point, we say that the data set is informationally complete, or IC in abbreviation. So in this way, the number of probe states, or LIC, denoted here, can be greatly reduced. The way this certification works can be broken down into two stages. So initially, whenever you measure a probe state, you will always get data that are noisy, right? So the first step would be to process the data and obtain physical probabilities. This will ensure that all reconstructions obey the correct quantum constraints. Now there are a few choices, but as an example, we compute the least squares probabilities subject to the POVM constraints. That is, all POVM outcomes must be positive and sum to the identity. So the point is this: if you use an insufficient number of probe states, then you will not obtain a unique POVM reconstruction. Instead, there will be a convex set of POVMs consistent with the least squares probabilities. So the next stage would be to estimate the size of this convex set naturally. And if the size is 0, then the measured probe states will give a unique reconstruction. We can, in fact, formulate this size estimation as a semi-definite program as shown in the second column. So, given the least squares probabilities computed from the data, we define a set of full-rank randomly generated operators Zj and optimize the linear trace function f defined as shown here, subject to the least squares constraint and POVM constraints. If we define further another quantity called SCVX, which is the difference between Fmax and Fmean, then one can show that in fact SCVX is a monotonic function with respect to the size of the convex set. In particular, if SCVX equals 0, then the convex set is a single point and the reconstructed POVM is unique. Now, we note that this procedure needs no assumptions about the unknown POVM. In fact, the lesson here is that the data actually encode more information than what was being used previously in naive reconstruction schemes. The uniqueness certification simply studies the data more closely and extracts this information. Right? So this is how we can perform compressive characterization reliably without resorting to unnecessary prior information about the unknown measurements of interest. So we first test this compressive power of CQDT with simulations. In this slide, we look at the performance using random entangled probe states. So panel A shows the LIC scaling behavior, which is again the number of informationally complete probe states you need to uniquely characterize the POVM with a fixed number of POVM outcomes. So we see that for rank 1 POVMs, we only need 4D-4 probe states to uniquely reconstruct them. This is actually a linear scaling in the dimension. So there is also clearly a larger reduction in LIC as the rank decreases compared to the D-square scaling required when certification is not employed. So panels B, C, D show the scaling for different number of outcomes and given POVM rank R. So the dashed curves in this figure are just benchmarks predicted from classical phase-retrieval problems. So these are problems related to the reconstruction of emission observables with intensity measurements. These are basically cousin problems to CQDT. Now, the results in these panels show that in the presence of the POVM constraints, the LIC can scale better than the classical scaling. The reason is that the quantum constraints heavily restrict the admissible convex set that are consistent with the data. So, therefore, the compressive behavior can be enhanced this way. Now, for the other numerically calculated formulas, I got them by numerically fitting the m equals 3D points, data points to arrive at the asymptotic behaviors. So another point I would like to make actually is that for low-rank POVMs, the classical benchmarks are already thought to be almost optimal. This also means that random probe states are sufficient to achieve near optimal compression. So what really shines in CQDT is that even random product probe states are roughly just as compressive, right? As shown in this figure. Now, on hindsight, this should not come as a surprise because linear algebraically speaking, one can always find orthogonal product bases. So similarly, linear independence has nothing to do with entanglement, basically. Now, this also implies that we can use product states to do CQDT, since these states are so easy to generate and require the requirement of a well-established set of input prop states for CQDT or QDT for that matter is not a very expensive one at all. So, because now we no longer need sophisticated entangling gates to generate these prop states. So finally, I would like to just show you the first experimental results for CQDT we have obtained from photopolarization setup over at Roma Tre. We have to thank Roma for the really expedient process in collecting data. So in this experiment, we first considered 8 unknown 2-qubit POVMs that are all minimally complete. That is, the number of outcomes equals 16. So 4 of them are rank 1, 4 of them are rank 2. Using random product polarization states, we managed to demonstrate a 37.5% compression for R equals 1 and a 12.5% compression for R equals 2. Right? So, which is not so bad, but not as dramatic as the next example. So, we now look at 4-qubit POVMs of a similar formulation. So, again, with random product probe states, we now find that in fact there is a 78.5% experimental compression for rank 1 POVMs and 74.6% compression for rank 2 POVMs. So we note that the corresponding POVM fidelities are slightly lower, so the LIC values are not as accurate compared to the simulation values, but the overall compression performance is clear. We have to recall that 4-qubit POVMs contain, for the minimal case, contain actually 256 outcomes. So this is actually a huge compression we're talking about. So with that, we can now conclude that from all experimental confirmation of compressive tomography, including the ones discussed today, there is at least one important lesson to be learned. Now, the idea of using data just for reconstructing some point estimator like the quantum state, quantum process, or quantum measurement should already be the thing of a past, because there is actually so much information encoded in the data that we are wasting by doing so. What we should do, in fact, is to extract this information and learn something more about the quantum system. And as far as informational completeness is concerned, this can be done with simple optimization schemes, like the semi-definite program that I have talked about in this talk. So in all of our published works, we have in fact shown that by extracting more information from the data, you can significantly reduce resources needed to characterize the quantum processor in general. So there will be more projects related to compressive tomography applied to, say, interesting quantum optical platforms and new applications pertaining to machine learning. So stay tuned to the archive for upcoming results. With that said, I would like to wish everybody happy holidays, stay safe, and obey social distancing, and let's have a much better 2021.